So welcome back to lecture 5. So last time we talked about discrete symmetries. We started with parity. We saw that the strong force and gravity and electromagnetism respect parity as a symmetry, whereas the weak force we just started to see actually maximally violates parity. And we encountered the tau theta puzzle, from which we learned that you can assign intrinsic parities to particles which are represented as quantum states, right. And we saw the intrinsic parity of a photon was -1, of fermion antifermion pair was -1 and so on, right. We motivated the intrinsic parities of these. Of a meson was -1 power L plus 1, and from which we got that the intrinsic parity of pions is -1. So let us further explore the theta tau puzzle and its consequences. Okay. We got to the point where we wrote down the intrinsic parities of the tau and theta. Remember that the theta goes to 2 pions with correct charge assignments, and the tau has intrinsic parity of -1 because it goes to 3 pions, right. Good. So that was the puzzle really. Why do these two particles have everything the same except parity? That really was the puzzle. Okay, people had discovered a host of mesons at that point, hadrons in general, a huge spectrum of hadrons, but they had never seen two mesons, completely different, two different mesons with exactly the same mass as far as can be told by experimental precision. Okay, so what is going on? So the resolution came in 1956 via C. N. Yang and T. D. Lee. Okay, and their radical proposal was that since everything but parity is the same for these two species, you know what, maybe parity is not a good symmetry. That was their resolution. Okay, why are we holding on to parity really? Why should everything look the same in a mirror? Okay, so and then they said maybe theta and tau are the same state. All right, it's just that we shouldn't expect sometimes the state whatever it is goes to 2 pions, sometimes it goes to 3 pions, and then if we don't assign an intrinsic parity like this, then we are fine. This was their radical proposal. Not only that, they also proposed a test for this, a laboratory test for this, okay, which went on to become particle physics legend. Okay, when it was conducted by that very year by Madame Wu. All right, and the punchline is that they were proved right. Okay, this test showed that they were indeed right, which shocked the world. It shocked the world so much that in 1957 they got the Nobel Prize. This is, I think, the fastest Nobel Prize that I encountered. Within a year of publication, and that very year they got it tested, they got a Nobel Prize. Okay, so what was the test? So it's actually very simple at face value, but it's a little subtle, okay, to think about. The idea was you take a nucleus that was known to emit electrons via beta decay, all right. In this case it happened to be a cobalt 60 nucleus, right, and the nucleus has an intrinsic spin, right. This is not really how spin works. The quantum spin is not a physical spin, it's its own quantum number, but for the purposes of this illustration just think of it this way, think of this toy model. Okay, okay, so the nucleus has a spin, and just to orient ourselves, let me call this north. This will come in handy later. Okay, I am going to call the upper direction north. Now Yang and Lee proposed and Wu found that if parity is a good symmetry, okay, then I should expect the electrons that are emitted by this nucleus to come from both the northern direction and the southern direction. Okay, let me just write it this way. Expect if P is good. Okay, why is that? Because if you flip this in a mirror, right, then what has happened now? So the north is defined by the spin actually, correct? In a mirror now, you are spinning in the other direction, correct? That means I should define north in this direction, and if parity is conserved, then it doesn't matter actually. So I would basically have let me use black, oops, electrons being emitted both in the northern and southern directions, right? Okay, now what happens if parity is not good? Okay, what happens if parity is violated? Then even if it is violated by a little bit, I would expect the following, correct? I would have in the mirror, since it is all flipped, so let me extend this. If I had more electrons from the northern direction and less in the southern direction, correct, in the mirror I would get less electrons in the northern direction and more in the southern direction. Do you agree? And if you take this to the logical extreme, in the maximal case, in the maximal violating case, I would have electrons coming only from the southern direction. That would mean that in the mirror electrons would be emitted only in the northern direction, right? So just like that, if I were to observe electrons only in the southern direction, I know that parity is maximally violated, because in the mirror it comes only in the northern direction, right? And this is more or less just what Wu found, that the cobalt nucleus is emitting electrons exclusively from the southern direction. Okay, so in one simple but subtle stroke, the maximal violation of parity was established in the weak interactions. Why? Because nuclear decay to electrons is through beta decay, which is a weak interaction. Correct? So the underlying decay is this basically, right? Which is beta decay, weak interactions. Okay, I hope that's clear. All right. Okay, so with this in mind, let's move on to the concept of helicity. All right, so we just talked about that. When we say helicity, think of screws, right-handed screws, left-handed screws, and you won't go wrong. Okay, so in a particle context, let me write it this way. If I have a particle moving in this direction, some velocity, and its spin, okay, I don't know how to undo. Okay, good. Okay, let me draw it again. I'm sorry. So, I'm losing colors now. Okay, and I had a spin such that the spin axis is pointing in the direction of the velocity. What is this? Is this right-handed or left-handed? This is what you would call a right-handed screw, right? So this is right-handed. Very good. And then if I have again spin oriented in the same direction, but if the particle was moving in the opposite direction, now the spin and propagation axes are in opposite directions. So, I would call this basically left handed, right. What I can also do is you know I can define the helicity like this, right. I can take the z component of the spin, and then I can think of this as the z component of the spin that is either aligned or anti aligned with the velocity, setting of course the velocity to be in the z direction. Okay, so I can either talk about this in terms of right handed and left handed helicities, or I can say helicity plus 1, helicity minus 1, same thing. Okay. All right. Can I do this for massless particles though? Is it kosher to do this for massless particles? What do you think? Can I assign a helicity of plus 1 and minus 1? Is that true? Because I'm sorry. Let me change the question. Can I do this for massive particles? Is what I meant actually. For massless particles, you can. Yes. We do know that photons have a right circular polarization, left circular polarization. Yes, indeed. I meant for massive particle. What distinguishes massless and massive? Think of it in a relativistic sense. Okay, so for a massive particle, I can always boost to a frame where I flip the velocity. Correct? I can always go to an inertial frame that's with its speed larger than the speed that you see here in a lab frame, so that now the particle seems to be going in the other direction. So, just like that, by going to a different frame, I have flipped the velocity, and we know that all inertial frames are on an equal footing in relativity, right. So, since we are dealing with a relativistic theory here, since we know that relativity is here, we cannot really treat this as fundamental, helicity as fundamental, okay, for massive particles. So, what we would rather do is define something that is actually friendly to this Lorentz transformations, to Lorentz boosts, and that concept is called chirality. Okay, let me just write for Lorentz invariant treatments. Okay, good. So, just keep this in mind. You will encounter chirality in a lot more detail when we talk about spinors and so on, okay, in the in-field theory. Of course, helicity equals chirality for massless particles, that goes without saying, right. Okay. Okay. Now, that means we talked about neutrinos last time, right. So, neutrinos actually almost fit the bill here. Neutrinos almost have a proper helicity. Why? Because neutrinos are severely light particles compared to other particles that we know of. They are mostly relativistic. In most scenarios, they seem to be relativistic, super relativistic. Okay, there is only 1 or 2 scenarios that I know of where they are non-relativistic. So, they have a very small mass. Their mass is known to be smaller than about 0.1 electron volts. So, to all practical purposes, they seem to come with a definite helicity. Okay, especially in the context of non-relativistic quantum mechanics, they do come with a definite helicity. Okay, so said differently, neutrinos are seen to be left-handed, and antineutrinos are seen to be right-handed. Okay, all neutrinos seem to be left-handed. any neutrino that we have measured so far has been left handed, because it is hard for us to boost to a frame to see them as right handed, okay, because they are all more or less relativistic. So, for all practical purposes we can talk about helicities of neutrinos as opposed to chiralities. This also tells us another thing, right, that clearly the neutrino is the face of the weak force, right. Clearly this is where you see the maximal violation of parity, right. It is not, there is no intrinsic parity to it, they come exclusively in one handedness and so on, okay. All right. So, how do we infer this? How do we, I think someone asked this, how do we infer the intrinsic parity of the neutrino also, for instance? How do we know it is left handed, for instance, right? We are not going to go and actually measure its helicity. We do not have a corkscrew to go and measure its helicity, right. So, what do we do? So, what you do is to inspect decays of particles that produce neutrinos, okay. For instance, the classic way to do this is to take a pion, okay, and you know that a pion would quickly disintegrate to a muon and an antineutrino with muon flavor, okay. So, I am going to draw that decay here. I am going to call this the antimuon, and I am going to call this, oh I am sorry, okay, the muon, that's antineutrino and that is the muon, okay. So, what have I done here? I have made use of the fact that the initial spin is the final spin, okay, and the initial spin is the spin of the pion, which is 0. We just saw that the L is 0 for pion, so S is also 0. The initial spin is 0, and I know that these are fermions, right. So, along this axis they would have spin half. So, I know that they have to have opposite spins, correct. That is why I drew them this way, I put opposite spins here, right. And of course, the velocities are taken care of by momentum conservation, right. Okay. Now, suppose you had this setup and you found that all the muons that you get, right, are right handed. Suppose you find that to be the case, right. It automatically fixes the handedness of the antimuon, the antineutrino also, right. Why is that? Because I need not have drawn the spins only in this way, I could have drawn the spins like this also, right. This is also possible. So, there were two possibilities for the helicities of the final states, right, except that we see that the helicities are have to be the same, right, for the two final states. The muon helicity should be the antineutrino helicity. So, if all the muons turned out to be right handed in your decay process, then all the antineutrinos are also right handed, right, and that was exactly what was seen. It is exactly what is seen also, okay. So, all so, okay, all muons right handed implies all antineutrinos right handed. And similarly, if I had started with this decay of the positively charged pion, where I have an antimuon and an actual neutrino, then what was seen is that all antimuons were left handed so that all the neutrinos are left handed. Okay, just the converse of this. So this is how we knew that, this is how we know, not just from this process, from many different kinds of decay processes, from many other scattering processes and so on, we know that neutrinos are left handed. Okay. Now here is another sanity check. There is also the neutral pion, right? Okay. So what about this? What would you expect? Would you expect the final state photon to be left handed or right handed? By the same logic, they should have this, the two photons, if I call them gamma 1 and gamma 2, right, should have the same helicity, right, by the logic from the previous page. They should have the same helicity by spin and momentum conservation, right. But would you expect them all to be just left handed, just right handed, or what? Okay, so neither. You would expect equal numbers of left handed and right handed photons. Okay, so let me just write that down. Equal, let me write it down differently. So the number of right handed pairs of photons will be the same as the number of left handed pairs of photons. Now why is that? We just saw before that, you know, the final state exclusively picked right handed fermions, exclusively picked left handed fermions, but over here we just changed our, you know, why are we saying that you can have equal numbers? That is because the previous case happened through the weak interaction. Okay, you had neutrinos in the final state. When you have a neutrino, that should tell you that there are weak interactions involved. Okay, so this might be a little early to draw Feynman diagrams, but you know, you can get some intuitive sense of what's going on if I draw it. So over here, the pi minus, right, is a u bar d, and the final state is mu on and antineutrino, and what had happened was you had exchanged W. Okay, so again W is a telltale sign of weak interaction. W is the mediator here. Okay, so this happened through the weak interactions, whereas this one, so this one I am going to draw a little differently, by and large happens through the electromagnetic interactions. The pion going to photons, even if I did not draw the Feynman diagram, it is probably easy to see that there is electromagnetic interactions involved here. Okay, so these are fermions in the loop and so on. But even without the Feynman diagram, from the fact that there are no neutrinos and there is nothing funny going on here, it is probable to guess that the dominant decay channel of the neutral pion to two photons happens through electromagnetism, and electromagnetism respects parity, right. So this is how we infer the underlying symmetries of the world. Okay. Okay. Now from the story of the pion, the you know, from pi plus and pi minus, right, there is something that you would have, you know, already got a hint of, which is that the pion, the pi plus went to mu plus and uh, the muon neutrino, the pi minus went to this, right. Okay, and then this one exclusively picked left handed fermions and this one exclusively picked right handed fermions, right. But what if I had intrinsically switched these two? So what if I no, let me say it differently. So I have these two processes. Now I look at these two processes and then if I just switch all the fermions with the antifermions, okay, I have an operator by which in these processes I just switch all the fermions with antifermions. I switch all the particles with the antiparticles in fact, right. Then nothing really happens, right. So what has happened now is, so let me write it this way. I am going to call this operator charge conjugation, where I am flipping all particles with antiparticles, right. If I do that, all that's happened is the pion has gone to this and I am just exactly flipping everything, right. It looks trivial but it is not quite that. And then by the same logic I should have right handed here and left handed here, right. So that shows that if you involve if I put parity and charge conjugation together as a combined operator, then nothing really happens to the entire system, right. Okay, said differently, the combination CP together seems to restore the weak force, right. Okay. So okay, the operative word here is seems. Okay, we will see later that even this combination turned out to be violated in nature. Okay, but for now we can see that sometimes a single operator might be violated in some interaction, but maybe some combination is still preserved. Okay, we will see variations of these as well. Okay, so that gives me my segue to the concept of charge conjugation. Yes. Okay.
Yeah, just a reminder, sir.
Okay. So I'll just wrap up in 2 minutes then.
Yes, sir, sure, sir.
Okay, sure.
Just a
Okay.
reminder, sir.
Okay. Okay, thanks. Okay, so we will wrap up soon by after introducing the concept of charge conjugation. So why is it called charge conjugation? The idea is to flip all charges. Okay, what do I mean by that? In this course we will be very careful about using the word charge. We will not be using that to denote only the electric charge. We will encounter other charges as well. Okay, things like baryon number, lepton number, other global charges and so on. Okay, even things like fermion number and so on. Okay, and of course electric charge, we will have hypercharge and so on. So you flip all the charges more or less. That is why people call it charge conjugation. More precisely, you take particles to antiparticles. Okay, but we will see an even more precise definition of charge conjugation. You need to define charge conjugation eigenstates. There are charge conjugation operators both in the non-relativistic and relativistic senses, and that will give us an even better definition. Okay. So to wrap up very quickly, let us go back to the Lorentz force. Okay. So I have this right. Under charge conjugation, what happens to charge? That is simple, it goes to the minus of itself, good. What happens to the electric field under charge conjugation? It goes to the minus of itself actually. You flip the charge to its minus, right, then the electric field lines turn around, right. So, it goes to the minus of itself. And what about magnetic field? It also goes to the minus of itself. Again you can see this in Biot-Savart law. The current now moves in the other direction if you flip the sign of the charge, and the magnetic field also flips, right. So, so this is a way to see that electromagnetism is invariant under charge conjugation, because the right hand side did not change sign. You know that under charge conjugation the force should not flip sign. So, okay, alright, good. So, we will explore this concept further in the context of other forces and especially the weak force and the strong force. Okay, thank you then, see you next time.